Hi, this is Kan-Lin speaking. I'm from the Department of Energy Engineering, National United University. In this renewable energies unit, this section is concentrate on the wind turbine. In this one, because time limit, I'm going to only briefly introduce the basic wind turbine, basic ingredient, principle, those kind of things. If you want detail, please take a course about the wind turbine and other corresponding courses. There's many types of wind turbine and depends on how to classify them. Over here, most common to classify the wind turbine is called a vertical axis wind turbine and horizontal axis wind turbine. The vertical axis wind turbine is a VAWT. Actually, you can see is a blade is around the vertical axis. And then on the right hand side, the wind blows in one direction, and then the turbine start rotating. But you can see the turbine, some is follow the blow of the wind direction, while some are against the wind direction. So some will be will convert the kinetic energy of the wind into mechanical energy rotation, but some blade may be cancelled out. The advantage of this kind of VAWT, the vertical axis wind turbine, is that it doesn't matter where the wind blow, where the direction of wind blow, they always will rotate and generate electricity. But the disadvantage is because the sun blade is move against the wind, so actually will cancel out some the mechanical energy. So the energy conversion efficiency of this type of wind turbine is relatively low, but the mechanism is much simple. Had a blade and a generator. Between the blade and the generator, there's a gearbox. Because the blade only rotated at several RPM per minute, but the power generator need to run at a few thousand RPM. So in order to generate enough profound electricity, so there's a gearbox to transfer the low rotating speed of the blade into the high rotating speed. The called vertical axis wind turbine because the rotation axis is vertical. That's why we call the vertical axis. Converse to the vertical axis is a horizontal axis. They also had a blade, gearbox, and a generator. But this type of vertical axis wind turbine, the blade had to face the wind in order to get a maximum power generation. So you need some kind of measurement for the direction of the wind. So like on the left hand side, they need a tail fin to direct the wind turbine so the blade can face the wind directly. So the mechanism is more complicated than the vertical axis wind turbine, but the efficiency is much higher. The reason called it a horizontal axis wind turbine because the rotating shaft is a horizontal, parallel to the ground. The type of the wind turbine, there's many type of wind turbine, depends on how to classify. Based on axis, there's a horizontal axis wind turbine, vertical axis wind turbine. And based on the blade, number of blade, then be 1, 2, 3, there's many. But most common is a 3-blade wind turbine. And the power rate depends on watt for the home usage, kilowatt for a small community, to the megawatt for the large community, megawatt. And then the location where to locate on the land-based wind turbine, or the offshore around on the sea, the offshore wind turbine. And then depends on blade size, then maybe the radius may be from 0.5 meter all the way to 100 meter or above. The progress wind turbine, they started in 1970s, and from a small wind turbine, gradually increase the size of wind turbine. So nowadays, maybe go to the diameter of the rotor diameter, maybe all the way go to 250 meter. It's a very large, maybe bigger than a football field. And then the power rating may be all to 20 megawatt higher. But right now in Taiwan installed somewhere around 2 megawatt, all the way maybe recently installed offshore in Holong, maybe somewhere around 6 megawatt to 8 megawatt. In the future, probably they will install much higher, larger wind turbine. Because if we install larger wind turbine, the cost for the installation is much lower per megawatt wind turbine. But you want to install a larger wind turbine, usually materials, design, or the structure, those kind of things had to be more engineering, because more larger, for instance, blade, the centrifugal force will be enough to tear down the blade, and the magnetic strength also had to be considered. So had more engineering into the when you build a scale up to make a larger wind turbine. Also transportation, installation also become an issue for such a huge stuff try to move around on the land or over the sea. And then this is typical the distribution of wind speed, but this one just theoretically think by the possibility of that, but nothing talk about that, I think. But for actually the wind turbine, the operation range, you may see that you can divide into low wind speed, medium wind speed, and high wind speed. On the green curve, this one is the ideal curve. Assume the power output for a given wind speed. That means all the air kinetic energy was converted into electricity. That's a green curve show up. But the blue one is actually possible the power output from the wind turbine, because there's an energy conversion efficiency. You may not capture all the wind, the kinetic energy. And the red one actually is the actual wind turbine output power. At a lower wind speed, usually the wind turbine was shut off, because actually running wind turbine needs some electricity, and a lower wind speed they won't generate too much electricity but consume more. There's no point in running that. And then at the extremely high upper limit, they also had a limit, because for the safety or the power output limit, so they will restrict the wind turbine to a certain output power. They either to slow down the wind turbine rotating speed, or put a brake on the shaft, and those kind of things to restrict the output power. So only in the middle range is that's a red one. Red line is actually represent actually possible wind turbine output power. How is it come from the power output from wind turbine? This one, the kinetic energy in the wind is 1 over mv squared. The m is a mass of the air, and then the mass flow of the air, dN over dt, equal to rho a dx over dt. The dx dt, that's been the velocity of the wind, the v. So for a given time, how much mass, air mass, flows through the wind turbine blade is given by this dN over dt. With these two equations in mind, we can calculate the output of the power. The power is equal to dE over dt, unit time the kinetic energy change. So you differentiate the energy, kinetic energy, we end up with power. So substitute dN over dt into this equation, we got the power output for wind turbine. This is a typical ideal case. The P equal to 1/2 of rho A V Q. The rho is the air density. The area is the area intercepting the wind. That's mean the blade, rotor blade. The V is the wind velocity. This is the ideal case. But in reality, there's a conversion efficiency. So we had a power coefficient on this diagram on the right-hand side y-axis. You can see the power coefficient, the black letter. And then the black curve represents the power coefficient at a different wind speed. And then the red curve represents the wind turbine power output. This one is calculated by this equation. The different from previous equation is ideal case. This equation we put the CP, the power coefficient, into calculation. The CP is a function of velocity. So different velocity, there's different CP value. Substitute into the equation, you can calculate the wind turbine power output. We end up with a red curve. But on the upper limit, the output power is flat because that's restricted by the wind turbine output power. It's not by this equation. This is artificially I just cut out. Do not let the power keep increase. And with a different heights, the wind turbine you install at a different above the ground, then the wind speed actually different. So this make a correction. At the high H0, original high H0, the velocity is V0. When you move the wind tower above ground at the H, the new high, then velocity go to the V. So that's a relationship is given by this equation. And alpha is a surface roughness exponent. It may be any range from 0.05 to 0.5. 0.05, that means a very calm ice, a patch of ice, and it's smooth surface area, so there's no surface friction, then the alpha is very low. If alpha is very rough, like the wind blows through a forest or the bushes, then it very strongly depends on the height. So this one just do a calculation, assume the alpha equal to 0.14 is for low grassland, and with a different velocity and normal the power velocity. This is a Taiwan wind turbine installation condition. In the year 2012, the total installation is 621 megawatt. And then by year 2015, in a near shore, offshore, there's 4 wind turbine was installed. And the year 2020, there's another about 300-400 megawatt wind turbine was installed in the Miaoli area. In the year 2012, all the installation is a land-based wind turbine. In the year 2015, most started offshore wind turbine. And hopefully by year 2030 or 2025, we hope the installation will reach land-based 1.2 gigawatt and offshore 3 gigawatt. So far, we almost close to 1 gigawatt already. So that goal may be able to reach by year 2025 or 2030. But the solar power may not be able to reach, I think. The key point of this unit is a type of, we describe type of wind turbine and the calculation procedure or the equation used for calculate the output power of wind turbine. And then we also give an example the effect of power factor and the tower height on the output power. Now the exercise, we like you to calculate for a blade with a 35 meter blade, calculate the power output at a different velocity. The power coefficient was also listed on the table. You can please fill out the table and then the diagram, plot on the diagram, and which I enclose with this class and return back to me.